Hi everyone, welcome back to the channel Coding with Bharat. So today we are going to take up the fourth problem of the last bi-weekly contest 121, which was count of powerful integers, right? So as you know, I was an avid competitive programmer during my college days. I'm a candidate master at Code Forces. I enjoy teaching a lot, and that's why I have tried to open this channel. So here we do not just discuss the solutions, but we also try to extract out the knowledge bits which we can use in other problems as well, right? So stay tuned. Let's discuss the problem. If you want, you can like the video and subscribe to the channel. And yeah, without waiting any further, let's start with our discussion. So let's go to our problem statement first. So this problem statement says we need to count something known as powerful integers. So what is a powerful integer? They have defined a powerful integer as something being positive, a positive number x. That number should end with a string s, or it should have a suffix of s at the end. So for example, if my s is 124, then any number like 124, 2124, 3124 up to, or even things like 723, 124, as long as they have 124 at the back, they are powerful integers. Okay. There is one more condition given, which is each digit of such a number should be within a given limit. So let's say if limit is 4 here, a number 5124, although has 124 at the back, is not powerful because it has a digit 5, which is more than this given value 4. So yeah, if we look at this particular scenario, we need to find powerful integers between 1 and 6000. So ideally, they would be what? They would be 124, then 1124, 2124, 3124, 4124. 5124 should have also been there, but because it has 5, it is not counted. So that is why you see these are the numbers which are counted and we have output as 4. So given limit, suffix, start and end, we need to find number of powerful integers between start and end. Let's also quickly look at the constraints of it for a moment. Start and finish can go up to 10 to the power 15. So they'll not fit into int. They will actually go into long, first of all. Second, they will have up to 15 digits, right? So very, very important. They can have up to 15 digits. Okay. So with all this in mind, let's think about the first approach, the absolute brute force that even you guys, I'm sure, will be able to think about. So just pause the video for a moment and at least come up with a brute force. Okay, so let's start discussing our brute force. The absolute brute force could simply be if we go and iterate from start to finish, look at every number, extract out their digits, and check two things. First, every digit should be within the limit. Second, the last digits equal to the length of s. So whatever the s dot size is, let's say it is 3. So last 3 digits, they should be equal to this given string s. So very important. Let me adjust the screen a little bit so that things are clearly visible. Okay. So yeah, two things. First, all the digits should be within the limit. Second, that last few digits that are equal to the size of the string, they should be exactly equal to s. Okay. So yeah, this could be the absolute brute force. But since our numbers are up to 10 to the power 15, this would in fact not work, right? This would not definitely work. So a slight improvement that some of you might have thought further from this, we already know the suffix, which is 124, let's say. What we can try doing is, we can try to generate all the possible, you can say, powerful strings. How? We can add a 0 here. Then we can try to add 1, 2, 3, up to limit. Once we are through with that, we can again start adding one more digit. So in a way, 15 times, because 15 is the maximum limit, 15 times we would try to add some 9 digits. So if we talk about the number of combinations, then there are 15 places. Each of the places might have 10 digits. So yeah, sorry, 15 places, each of them might have 10 digits. So 10 to the power 15 possibilities are still there, but yeah, in some of the cases this might work slightly better and might be slightly optimized, right? Because we are not going through extra numbers which do not have this as suffix. Yeah, but any of these two would not be sufficient to pass our given time constraints. So then how do we go about it? So let me talk through first an important pattern, right? Which is whenever we are told to find something in L2R, right? Whenever we are told to find something into L2R, and that operation, the thing that we are trying to find is invertible. So let me talk about what is invertible. So let's think about sum, right? So let's say you are given an array, and let's say you are asked find the sum from L to R. Then if you have multiple queries like this, one optimized way to do this is to calculate prefix sum. I'm sure a lot of you might be aware of this technique. So 3 plus 3 6 plus 4 10 plus 5 15. And then instead of calculating L to R sum by iteration, what you say? You say give me the sum from start till R, which is this 10, and I will subtract or invert or remove all the things starting from start till L minus 1. So that is this sum, which is 2. And that will automatically give me the sum of these three numbers. So whenever we have an invertible operation and we want to calculate its value in L to R, a way to look at it is find the answer up to R and subtract the answer up to L minus 1. So similarly here, if we want to find the powerful integers between L to R, what we can do? We can just try to calculate powerful integers up to R and then subtract out the number of powerful integers up to L minus 1. So yeah, very similar to the prefix sum technique. This technique is always and always possible with invertible operations like sum, count, XOR, right? But if we talk about max from L to R is not dependent upon max from start to R and max from start till L minus 1. So because max is something which is not revertible. So very important, a common pattern that we would see in a lot of other questions as well. Cool. So now the problem reduces to given a particular value R and limit and S, find the number of powerful integers up to that point, right? So let's start our work on that. So let me ask you a question first. Let's say my suffix was 124 and let's say my limit for which I was calculating or my R for which I was calculating powerful integers up to was something like let's say 5 times 0, 1 2 3 4 5, yeah, 5 times 0, right? So forget about the limit for now. Let's say we are playing limitless rise of now, or limit is equal to 9, so we can take any digit that we want. So let's forget about that. Can you come up with how many powerful integers would be there up to this value having 124 at the end? Okay, so just pause the video and think for a moment. If you were able to think, well and good. Otherwise, let's start discussion. So let's say we put 124 at the last three ends. Now, I want to calculate value up to 5 and followed by 5 zeros, right? So if I think about the first digit, any value smaller than this 5 into 10 to the power 5 would either start with 4, 3, 2, 1 or 0. If it's 0, then that means we have one less, you can say, digit, right? But any value starting with 4, 3, 2, 1, 0, any of these five values, these five possibilities are there at the units digit. Then at the next two places, not the units digit, but the most significant digit. If we look at the next two, then we have all the 10 possibilities. So if I calculate the total, I can say it is 5 into 10 into 10 using permutation combinations. these many possible powerful integers which are smaller than this value, 5 into 10 to the power 5. What are these? If you think about it, I can take any values, right? For example, if I take 3 from here, out of these 10 I take, let's say, 9. Out of these 10, let's say I take 0. So 390124 is a possible solution. So you can pick any values from 0 to 4 for the first place, any values from 0 to 9 for the second place, any value from 0 to 9 from the third place, and that plus 124 will form a possible solution. Okay. So if we are just given our R as something like one digit followed by all zeros, the answer becomes very easy. How does the answer become easy? Last few digits equal to the suffix are fixed. They are fixed. Rest of the digits you can put any number up to 10. And the absolute first most significant digit you can put any value smaller than that. So 43210. If this was 6, then our possible options would be 543210, right? So let me formalize it a little bit more. If I have to come up with a formula here, then I can say if my S is of form x 0 n times, this is not x, this is actually your n. Let me say n here. The number, the r, n or r, whatever, the number for which we are calculating the number of powerful integers smaller than it. And let's say s is some value 124 of 3 digits. Then that means the answer for this particular case is what? You can take x options at the beginning, then 10 options for all the remaining except these many. So 10 to the power 10 to the power size of this n, so n dot size, minus size of s, and minus 1. Why minus 1? Because this x we have also included in our initial part. So for all the places except this one and these equal to s dot size, that all the places can have all the 10 values. So 10 to the power this much. So this becomes a mathematical formula to calculate number of powerful integers without a limit. Right now we have not considered limit, up to a certain value r, and that r is of the form x followed by some zeros. Okay, but our r can be anything, right? So for example, let's repeat the same question. S is 124, but our r is, let's say, 653 1 2 7. Now how do we go about doing it? Okay, so I would say this this would become like a recursive solution or solving the same problem again and again. So just pause the video and think if you can use the above logic to convert this into some form of a recursion here. Okay, great if you were able to do so. If not, let's just continue. So right now, let's take, first we are starting with 6. So any values having less than 6, we already know the answer, right? So up to this value, 6 into 10 to the power 5, we can easily calculate the answer. Now our concern is values more than or equal to 6 into 10 to the power 5. More than this, right? So for values more than this, if I think about, then in a way I am dealing now with this remaining part. So this 6 is fixed. Any value more than 6 into 10 to the power 5 will have 6 at the initial place. And we need to make sure whatever comes after it should have our suffix, and it should be within this range, within 53127. So in a way our problem becomes the same problem for 53127 because we have fixed this 6. So if we calculate the number of powerful integers up to 53127, let's say one of that is some value like this, 11124, 11124. Then I can just add a 6 there and it becomes a possible answer for our initial case. So basically, I can say answer for answer for something like 651324 can be written as answer for 6 1 2 3 4 5 plus answer for 5 1 2 3 4 plus answer for 1 0 0 0 plus answer for 300 and so on and so forth. So just individually for each digit we can know the size and that use that to calculate the answer. Okay, so now we have solved this question in a way without introducing our limit. So let's introduce our limit. So let's say here our S was 124. So when we make a call for answer 20, it will see that 20 is already smaller than 124. So answer for this is 0 and we can stop making our recursion further. Okay, so yeah, this is the termination case basically. We can keep on making recursion till we reach to a string which is having value smaller than this given value 124. Okay, let's talk about the limit now. Let's say in this particular scenario only, our limit was, let's say, digit uh, 6 for that matter, right? So let me just change it a little bit so that we can support the 6. Okay, limit is 6. So now we make a call for 6 into 10 to the power 5. We make a call for 5 into 10 to the power 4. Now we also make a call for 7,000. But we don't make a call for 300. Why? Because any number starting with 657, that is what our assumption was, right? We'll fix 6 now. Like if you go back to our previous assumption, the idea that we fix this 6 and then make a call for the remaining number, right? So in a way, when we are trying to make this fourth call, we are fixing 657, but we cannot fix 657 because this 7 in fact is more than the limit. So we stop our recursion as soon as we arrive at a digit up to this limit. So yeah, that is the major idea of this solution. Great. So if you were able to understand it, let's try to look at the simple coding part of it. So let me go back here. Let's go to our browser. Okay. Cool. First thing that I've done, I've tried to first iterate on the digits of this suffix. Let me check if the screen is visible. Iterate on the digits of this suffix. If any digit of the suffix itself is more than limit, then that means there is no answer. Why? Because the suffix needs to be there at the end. And if one of that suffix itself is more than the limit, that means there is no answer, right? So we have returned 0 in that case. Otherwise, what I've done is I've tried to write this formula that calculate the powerful digits less than this finish value minus calculate powerful digits less than this start value. So I've reduced it by 1 because if you remember the formula, calculate till r minus calculate till l minus 1, right? So let's now look at the calculate lesser function. Okay. So I made a case if the number for which we are calculating is smaller, is having less digits than our suffix, right? For example, our suffix is 124 and the number that we are calculating for is 20. So in that case, there is no possible answer because our number itself is smaller than the suffix. So if this happens, or if the number of digits are same but n is smaller than s, that is if the number is let's say 120 and the suffix is 124, then also the answer is 0. So there I have returned answer 0. Otherwise, if size becomes same, so let's say the number that which we are calculating smaller is 127 and the suffix is 124. So n is let's say 127 and suffix is 124. then that means there is one answer only, which is 124 itself, right? Even if we take a huge number like 999 here, then also the answer is still going to be 124 only, because anything addition to it, at least we need to add one more digit here. So if the size is same, return 1. Otherwise, I made two cases based on the limit. So if the digit that I encounter in the beginning is more than the limit, so for example, the case where let's say my n is something like 7123, right? And my limit is let's say 5, then that means I need not make a further call. I can just replace the first value with numbers up to 5, 0, 1, 2, 3, 4, 5. These 6 values. That is what I can put at the beginning. Remaining, if suffix is let's say 22. So remaining one digit, I can put anything from 0 to 9. So if I calculate the answer for this, what would it be? In the initial place, I can put 0, 1, 2, 3, 5. So 5 values, 0, 1, 2, 3, 5. Sorry, 0, 1, 2, 3, 4, 5. So 6 values. And at the second place, I can place anything from 0 to 9. So into 10. In the third and fourth place, I need to put 22. So the answer for this is just going to be 60. That's it. I need not make a further call for 100 because I cannot put 7 in the beginning, right? So what I've done, I've just calculated the power, keeping the first digit as limit plus 1, as you saw here. Limit is 5, so 5 plus 1, 6. That is going to be the first digit's possible values. Then for the remaining digits also limit plus 1. Oh, actually, yeah. So in the second place also, we cannot put all the 10 values. We can only put up to this limit. So this is again going to be 6. So limit plus 1 and then limit plus 1 to the power n dot size minus s dot size minus 1. So n dot size, which is 4, minus 1 because first digit we are calculating separately, and minus s dot size because those will be fixed with these values only directly, right? So n dot size minus 1 minus s dot size. The second case where we can make further call. For there, what we do, we first calculate the remaining string. We make a call for that remaining string here. And then do the similar operation for power. Okay. That at initial place, we can take any numbers up to that digit. For next places, we can take up anything up to limit. And again, the size remains the same. So recursion, simple recursion based solution, right? Where we make two cases, if it's greater than limit or if it's less than limit. So this is the case where we are dealing with something like, let's say 3123. Limit is let's say 5 and this is 22. So in this case, we do our first calculation. At initial place, we can have any numbers from 0, 1, 2. So 3 numbers. And that is what I've written here. N of 0 minus 0. That is 3 possible options here. Then any option up to limit in the remaining places. So 5 is the limit. So any of these 6 options can be at the first place. And rest 2 will be same as this 22. So 3 into 6, 18 here. Plus I have to make a call for fixing 3 here and then calling for 123. Because I have not considered cases like, let's say 3122 or 3022. That will be handled when I make a call for this 123, assuming that 3 is fixed here. So that is why this second call is there. Okay, power function is simple. We take the current digit and multiply it with the actual power function of limit and length. And this power function is simply by the divide and conquer approach that is there for power function. Okay. So that is the basic idea of this solution. I hope you guys can implement it. Let me also quickly talk about the salient points which you can keep in mind further for new questions. First point that I think I already spoke. Whenever we have an invertible operation, like sum, and we want to calculate from L to R, we can reduce it to sum up to R minus sum up to L minus 1. Second, whenever we are dealing with a number x with a lot of digits, 6, 1, 2, 3, 4, 5, something like this, then we can actually calculate first by only taking this 6 assuming 0, then only taking this one assuming 0, then only taking this 2 assuming 0. So this is also a common technique which actually also translate to a famous digit DP paradigm, right? Although digit DP was not required in this particular problem, some people have solved it using it. But yeah, this idea actually evolves into something like a digit DP. Cool. So do implement it. I'll attach the solutions in the description as well as the comment section as well. And if you like the video, do give it a like. And let's see you guys tomorrow with the new problem.